Okay, so up until now, we've looked at a few different formulas that help describe different types of motion that's happening. So we can calculate displacement, we can calculate distance, we can calculate speed, and we can calculate velocity. So there's two different ways we can do it. We can actually use formulas, mathematically calculate things, or we can actually take information, graph it, and then the graph tells us information about that type of motion as well. So today we're going to learn how to graph motion with constant velocity. So constant velocity means that our speed is staying at the same amount. It's not changing. We're not speeding up. We're not slowing down. It's constant. And so what that means in terms of the displacement in time, it means that every second we're moving the same displacement or distance away. Okay, and so this is what we do. We create a position time graph in order to interpret that information. And if it's constant velocity, it means that the position time graph is going to be a straight line. And so we're going to look at an example together to see what that looks like. So for example, an ostrich, the world's fastest bird on land, runs 18 meters per second west for 8 seconds. So we can take that information and break it down on a per second basis. So that's what we're going to do. Step 1, create a position time table of values. So basically we're taking over 8 seconds. We want to know what happened or report what happened. So 1 second, 2, 3, 4, 5, 6, 7, oops, and we need another column for 8. Okay, and basically it's saying that for 8 seconds it runs 18 meters per second, or every second it's running 18 meters. So if we were to report on its position, remember position is where you're located based on where you started. So at time 1, after 1 second has passed, we've moved 18 meters. And then after 2 seconds, we've run another 18 meters. So that's a total of 36. So each second, we're moving another 18 meters. So it just adds on. So our distance away from the start is an additional 18 meters every second. So 72, 90, 108, 126, and 144. So every second we moved 18 meters away in the west direction. So our position is telling us at each one of these seconds, this is how far we are away from the start or from where we started. So once we have a table of values, our next step is to graph position versus time. So a position versus time graph of the ostrich. Here's what we're going to always do. Time will always be on the bottom with our units in seconds. Position will always be on your y-axis or vertical axis with your units in meters, and because it's position or displacement, so maybe we should add that in. This is the same as displacement, and that's why it's a vector quantity, so we need the direction. Okay, so now you want to pick a scale for each of your values. So times along the bottom, we have to go from 0 all the way up to 8. So just based on the numbers that you have here, it's all going to depend on how you graph it. But in using this grid, we have starting at time 0, and we'll go up by 2s. So 2 seconds, 4, 6, and 8. Because what we have to do, what we have to keep in mind when we're making a scale, is it has to increase by the same amount each time, but it also has to reach as high as your highest number. So this gets us for our time. If we look at our position, we go as low as 18 all the way up to 144. So based on this graph, only having 4 divisions here, I'm probably going to stick with something like up by 50s. Ideally, it would be nice to have more sections, but let's just say we're going up by 50. 100, 150, and 200. So remember, when you're choosing your scale, you have to increase by the same amount each time, but how much you increase by is up to you. And the only thing you have to keep in mind is it has to go as high as your highest number for that scale. So now we've got our numbers on our grid. We want to plot these values. So at 1, we're at around 18. 2, we're at about 36. 3, we're at 54, and so on. And what you're going to see, when we have something that's moving at a constant speed, it's going to form a straight line on your graph. And the reason we do this is because this straight line, we can do something with it to find our velocity. So at 7, we're at 126, and 8, 144. A fairly straight line. This is tough to do on the computer. Okay, so with constant velocity, you're going to have a straight line. Once you've plotted your values, you're going to use a ruler, and you're going to draw a straight line through each of the points. It might not be perfect, but what we call this is a line of best fit. So you want a line of best fit to go through as many points as you can, having an equal distribution on either side of your line. So this line is going to represent the motion of this ostrich now. Okay? So you might be asking yourself, why did we make a graph of this? Because when we make a graph of constant motion, we can actually calculate the average velocity without using the formula, but using some information off of our graph. And that information that we're going to look for now is the slope of the line. So hopefully from grade 9 or 10 math, you remember that when we calculate the slope of the line, what we're looking for is basically just how steep that line is. So here's your steps for figuring that out. Pick 2 points on your line that you've plotted. So let's just say we're going to pick this one, and we're going to pick this one, and create a triangle from that. So from here, over, and here, up. Our slope, how steep the line is our rise. So how much did it go up over our run? How much did it go horizontally? So if we know what these numbers were, and we do because we plotted them right from our table of values, at 2, our value was 36. So this point is 36. And at 7, this point was at 126. So we can use this information now to figure out our change in vertical distance. If this line represents 36, our change in vertical distance, which is our rise, is the change in these two values. So 126 minus 36. That's how much it rose over that time period. And we want to divide that by how much it went horizontally, which is called our run. So we know this point represents 2. And this point here represents 7. So our change in horizontal distance is basically from 2 to 7. How much do we have to add to 2 to get to 7? Is 5, or 7 minus 2. Okay, so if we look at what the vertical scale is telling us, it's telling us our position, and that's measured in meters. And if we look at what horizontal, or our run, units are, that's seconds. So when we calculate our final answer, we end up with 90 over 5, and we end up with 18 meters per second. So why did we do this if they told us that it was 18 meters per second? Because I wanted to use an example. If we know the speed and it's running at a constant velocity or speed, then we can actually create a graph, calculate the slope, and double check our answer. Our slope should turn out to be the same. So this was in the west direction. Remember that this is what we've just found out is average velocity. That's a vector. So slope is equal to velocity on a position time graph when we have a straight line and constant velocity. So it's just another way of finding out the same information we did with the formulas. So we used the formula yesterday. Today we're going to look at the same type of thing using a graph. So what you're going to be expected to do is be able to take information in a table of values, or something like this in a problem, making a table of values, then graphing it. Once you graph it, be able to calculate the slope. And that slope, what does that tell us? It tells us our velocity.